Right, we have seen how molecules can be represented using Cartesian coordinates. But there's a more efficient way to represent molecules, and that is called the Z-matrix. And so I'd like to build up a Z-matrix for the water molecule that we had before, and it is quite straightforward to do so. What you've got to do in building a Z-matrix is we've got to pick up an atom to start with, and you label them 1, 2 and 3. I'm going to start with the oxygen atom as atom number 1, and then move to the hydrogen atoms as atoms number 2 and atom number 3. So the first row in the Z matrix is associated with atom number 1. So if I can label atom number 1, and then I can write the first row as being an oxygen atom. So the first row of that Z matrix is now sorted. Right, now the second atom is a hydrogen atom, and we've got to be careful with the hydrogen atom is that that hydrogen atom has to be positioned exactly the right distance from the first atom. So to build up the second row of a Z matrix, here's my second row. It is a hydrogen atom, and it's atom number 2. The bond 2 to 1 is this value, exactly 0.96. And that 2 to 1, we know it's 2 to 1 because it's the second row of a Z matrix, and we've written the number 1 telling us where the bond is 2. So that's the second row. And then finally, the third row of the Z matrix, the third atom is a hydrogen atom, and that atom is also bonded to atom 1 with a value of 0.96. But be careful, because this Z matrix is not complete, because the Z matrix could also refer to a molecule that looks like this, where the angle is not included. So we've got to be very careful to include at this point an angle to place atom 3 in the correct position. Okay, and so the way we do that is we say, well, we put it in a 2 to say it's the angle from 3 to 1 to 2, and then finally we put in its exact value as 109.5. And so we have built up beautifully the Z matrix for water. And it's not common to include these labels. We can remember these numbers by being the first row, the second row and the third row. So the complete Z matrix will look like this. I want you to have a look at the Z matrix and realize that there are actually only 3 values of importance in the Z matrix, and that's the angle and the 2 bond lengths. Of course, we need to know where they are connected to, those connections, but if you were trying to optimize this water molecule, you'd be trying to change these numbers to get the lowest energy conformation of a water molecule. There would be only 3 things you'd need to change to try and find the optimum geometry for that water molecule. Compare that to the Cartesian coordinates. If you were trying to optimize a water molecule represented by Cartesian coordinates, you would be changing 9 numbers to try and get that water molecule into the best possible arrangement. So the advantage of a Z matrix is that if you're working with Cartesian coordinates, you need 3 Cartesian coordinates per atom. You need 3n numbers to work with Cartesian coordinates. With a Z matrix, you work with many less. It's 3n minus 6. You can see we had 9 here, and 9 minus 6 is 3, so we have only 3 values to work with. With linear molecules, it's slightly more complex, and you have 3n minus 5 values. So the Z matrix is highly advantageous compared to Cartesian coordinates when you come to do calculations. So building a molecule as a Z matrix really is very efficient for later on. Okay, so yes, there's our Z matrix when we label the atoms that way. But what if we label the atoms in a slightly different way, or if we looked at a different arrangement of a water molecule? So over here, if I label the atoms as 1, 2, 3 as I did before, even in this arrangement we still get the Z matrix as we had before. But of course, if we label them slightly differently, you can see that the Z matrix changes slightly. We start off with a hydrogen atom. The oxygen is bonded to the hydrogen with a distance of 0.96. This hydrogen is now bonded to atom number 2, and the angle it makes then to 3 is 109.5. So we can have the atoms in a different order, but you'll notice that it doesn't matter with the order. The values you get in the Z matrix are all the same values. Okay, I'd like to look at a slightly more complicated example at maybe hydrogen peroxide. So here's hydrogen peroxide, and can we build up a Z matrix for hydrogen peroxide? This picture you can see is one conformation that's listed on the Wikipedia page for hydrogen peroxide. So to start off with, I want to just label all of the atoms. So I'm going to start off with the hydrogen as number 1, oxygen is number 2, oxygen is number 3, and hydrogen is number 4. And these are the values I've changed from picometers, which Wikipedia has, to angstroms, which is what we need for the Z matrix. So let's see how the Z matrix builds up. Okay, so we start off with the first row. Atom number 1 is a hydrogen. Then atom number 2 is an oxygen, and it's bonded to atom number 1 with a distance of 0.95. So we're building up our Z matrix. Then atom number 3 is bonded to atom number 2 with a distance of 1.474 angstroms. But of course the angle 3 to 1, this angle 3 to 1 must be 94.8. So row 3 to 2 to 1 must be 94.8. Okay, and then on the final row, this is not quite there. The final row, we've got atom 4 is bonded to atom 3 with a distance of 0.95. The angle to 2 is 94.8, which we've got in there. But be careful, we haven't taken into account this dihedral angle. So we're going to have to just think about this, and I'm going to draw this slightly differently. We've got to get that dihedral angle as being 115.8, and that dihedral that we want to define is the dihedral 4, 3, 2, 1. So that dihedral 4, 3, 2, 1 is simply this 115.5 degrees, and we include it in the Z matrix. Row 4 bonded to 3, 2, 1, so the dihedral 4, 3, 2, 1, and we can list its value as being 115.5 degrees. So this is as difficult as it gets with the Z matrix. We'll only go up to dihedral. So if you have a look at more complicated Z matrices, like for ethane, you'll see that the first row is an atom, then you've got second row is a hydrogen bonded to atom number 1 at a distance, hydrogen bonded to atom 1 at a distance with an angle 109.5, and then you will start to see that by row 4 you're starting to get these dihedral angles coming in. Have a look. Interesting. So you see this here, this row here is 1, 2, 3, 4, 5, 6. See, we're in row 6 here. So it's interesting to know that the 6, 5, 1, 4 dihedral is 180 degrees. Can we check that? 6, 5, 1, 4. And can you see the arrangement is 180 degrees for that? Okay. Just be careful, because in some cases the dihedrals don't follow bonds. If dihedrals don't follow bonds, like the 6514, it's termed an improper dihedral, but we won't spend too much time on improper dihedrals. So what we've done at this point is we've described building the model, and normally what we would do is we would use a mouse interface to click and build up a model, but it's always good to know that a model is built in 3D space, and so the model has 3D coordinates and it has Cartesian coordinates, and that's one way to represent it. However, we can represent molecules in a slightly different way, which uses less coordinates as a Z matrix. We start off with an atom, atom in a bond, atom bond and angle, and finally atom bond angle dihedral to build up a molecule. So in terms of molecular modeling, we've spoken of define the problem and build the model. This is the build model part, and we'll move on next to doing the calculations.